You know when your streaming app just gets you? Suggests the perfect show, like it reads your mind.
Mm-hmm.
Well, that's machine learning working its magic.
Mm-hmm.
It lets computers figure things out from data, make predictions, without needing step-by-step instructions for everything.
Yeah, it's like teaching by example, tons of examples, show it enough pictures of cats and dogs. Eventually, it learns to tell them apart.
And the more pictures, the better it gets.
Exactly.
Mm.
And today, in this deep dive, we're getting right into the engine room, the machine learning algorithms themselves.
We've sifted through a whole load of material on these algorithms.
Right, pulled out the key stuff, the essentials. Think of this as your fast track to grasping what makes this field tick.
So the plan today is to break down these algorithms. Like, what are they fundamentally? How do we even group them?
And crucially, where do we actually see them working? You mentioned streaming, but think sports predictions, medical insights, all sorts.
And the goal for you listening is to walk away with a solid, clear picture of these tools, without needing a PhD in computer science.
We want those aha moments, where the logic just clicks and you see why this stuff matters so much now.
Okay, let's start at the beginning then. Machine learning. What's the core idea? There's that old definition from Arthur Samuel back in the 50s.
Oh yeah, the ability to learn without being explicitly programmed. Pretty mind-blowing for the time.
Definitely. And Tom Mitchell updated it later,
Yeah.
right? Something about learning from experience to get better at a task.
Exactly. Experience E, task T, performance P. But practically it's evolved, hasn't it? Now it's more about, well, turning masses of data into actual useful information.
Or building systems that can tackle really complex stuff. Things that might even need human-level smarts.
Right. Complex pattern recognition prediction.
So doing all this heavy lifting is the algorithm. Sounds technical, but what are we actually talking about?
At its simplest, an algorithm is just a set of rules, a step-by-step process, like a recipe.
Okay.
But machine learning algorithms are special recipes. They can change themselves, adapt. As they process more data, they learn from their, let's say, past mistakes or successes.
They tweak their own settings.
Yeah, they adjust their parameters to get better at predicting what's coming next, based on what they've already seen. It's an iterative process.
Makes sense. But there must be loads of different algorithms. How on earth do you choose which recipe to use?
Ah, that's the million-dollar question. It's definitely not one size fits all.
Right.
The choice depends heavily on your data. How much do you have? Is it good quality? How diverse is it? And crucially, what are you actually trying to find out?
So the goal matters.
Hugely. Plus practical things like how precise do your results need to be? How much time do you have for the algorithm to learn the training time? How many data points?
Sounds like there's some experimentation involved.
Oh, absolutely. You often try a few different algorithms, tweak them, and see which one gives you the best performance for your specific problem.
Okay, so to get a handle on this zoo of algorithms, how do people usually categorize them? Are there main groups?
There are two really common ways to slice it. The first is by learning style.
How they learn.
Yeah. Does it learn from data that already has the answers labeled? Sort of like studying with a teacher, that's supervised learning?
Okay.
Or does it learn from unlabeled data, just exploring patterns on its own? That's unsupervised. Then you've got semi-supervised, which is a mix.
Bit of both.
And reinforcement learning, which is more about learning through trial and error, like getting rewards or penalties.
And the second way to categorize them.
Is by their function or what they actually do. Are they trying to predict a continuous number, like a price? That's regression.
Or put things into buckets, like spam or not spam.
Exactly, that's classification. Or maybe just find natural groups within the data, that's clustering, and so on.
But underneath all that variety.
Underneath, yeah, all machine learning algorithms have sort of three core components: how they represent the knowledge, how they evaluate how well they're doing, and how they optimize or improve themselves.
And remind us, why go through all this trouble? What's the big advantage of using machine learning?
Well, it shines when you have problems that need tons of manual tweaking if you tried to code rules by hand, or problems that are just too complex for traditional methods.
Like finding subtle patterns in massive data sets.
Precisely. Sometimes machine learning can even lead to less code but better performance because the system learns the rules itself instead of you having to write them all out.
Okay, let's dig into those learning styles. First up, supervised learning. You said like learning with a teacher or a textbook with answers.
Exactly right. Think about learning to identify different types of birds. With supervised learning, you'd get pictures of birds, and crucially, each picture would be labeled robin, sparrow, blue jay.
So the algorithm sees the picture and the correct answer.
Yes. It learns to map the features it sees in the image, like color, beak shape, size, to the correct label. The goal is to build a function, a model, that can do this mapping accurately.
And then you test it.
Then you give it new bird pictures, ones it hasn't seen during training without the labels, and see how accurately it predicts the species. This uses separate pest data.
Now, the source material mentions things like Q-learning under supervised. Isn't that usually reinforcement learning?
That's a really sharp point. Yes, Q-learning, temporal difference, MCTS, A3C, these are typically pillars of reinforcement learning, where agents learn through rewards. It's possible the source categorizes them based on some specific aspect or context, maybe how they use feedback that looks like supervision in some sense.
Okay, so a potential quirk in the source's classification there. We'll stick with how it's presented, but good to note. The key is labeled training data.
That's the defining feature of supervised learning, yes.
So what about unsupervised learning? That sounds more like discovery, learning without the answer key.
Perfect analogy. Imagine getting that same big pile of bird photos, but this time, no labels, none at all.
So the algorithm is just looking at the pictures.
Exactly. Unsupervised algorithms dive into the data looking for inherent structures, patterns, or relationships without being told what to look for. It might group the birds based on similarities in color patterns, size, or beak shape, effectively discovering potential species categories on its own.
Finding the hidden structure.
Finding the hidden structure, that's a great way to put it.
And then semi-supervised and reinforcement learning build on these.
Pretty much. Semi-supervised learning is the middle ground. You have some labeled data, maybe you know the species for a handful of bird photos, but most of your data is unlabeled. The algorithm tries to leverage both.
Uses the labeled ones to help figure out the unlabeled ones.
Kind of, yeah. It uses the labeled data to get started and then tries to intelligently apply that learning to the larger unlabeled set. And reinforcement learning, as we touched on, is different again. It's about learning optimal behavior through feedback.
Like training a dog with treats.
Exactly. The algorithm, or agent, takes actions in an environment and gets rewards for good actions and penalties for bad ones. It learns over time which actions lead to the best rewards. Think game-playing AI or robotics.
Okay, different ways of learning. Now let's switch gears to categorizing by function. You mentioned regression algorithms for predicting numbers.
Correct. Regression is all about understanding and modeling the relationship between input features, say, the square footage and number of bedrooms in a house, and a continuous output value, like its price.
So you can predict the price for a new house.
That's the goal. The input and output are typically numerical, and often we start by assuming a linear relationship, like a straight line on a graph.
And a common one is ordinary least squares regression, OLSR. You mentioned fitting a line.
Yeah, imagine you have a scatter plot of data points, house size versus price. OLSR tries to find the single straight line that best represents that data by minimizing the sum of the squared vertical distances from each point to the line.
Minimizing the errors, basically.
Precisely, the squared errors. It's straightforward, works well when the relationship is roughly linear, and can be effective even with smaller amounts of data.
But it has limitations.
It does. It's quite sensitive to outliers, those odd data points far away from the main trend. They can really skew the line.
Right.
It also assumes the relationship is uniformly linear across all the data, which isn't always true. And it performs best if the errors, the residuals, are normally distributed.
Okay. Then there's logistic regression. The name is confusing because it's often used for classification, right? Like yes/no outcomes.
Exactly. Despite regression in the name, logistic regression is a go-to for binary classification problems. Will a customer click the ad? Yes, no. Is this email spam? Yes, no.
How does it work if it's not predicting a number directly?
It models the probability of the outcome being yes or 1. It fits an S-shaped logistic curve to the data, mapping the input features to a probability between 0 and 1. You then set a threshold, like 0.5, to decide the final classification.
Ah, okay. So it predicts the chance, then you decide the class.
Pretty much. And like OLSR, it can be quite effective when the underlying assumptions fit the data, and it works well with relatively small data sets too.
Then we get into methods like MARS and LOW-S. Sounds like they handle curves better than straight lines.
They do. Multivariate adaptive regression splines, or MARS, is clever. It fits separate linear regression models to different segments of the data, sort of like piecewise straight lines or splines. This allows it to capture nonlinear patterns much better than simple linear regression.
So it adapts to bends in the data.
Yes. And LOES, or LOES, Locally estimated scatterplot smoothing takes a different tack. It's non-terametric. For any point you want to predict, it looks only at the data points nearby, fits a local regression model just to that neighborhood, and uses that to make the prediction.
It focuses locally.
Right. This makes it very flexible for fitting complex curves. You can even estimate the uncertainty around the fit, but the downsides are significant. It needs lots of data points, densely sampled.
Because it relies on local neighborhoods.
Exactly. And it doesn't produce a single neat mathematical equation for the whole curve. Plus, it can be computationally heavy because it's doing all these local fits.
Okay, moving on. Instance-based algorithms. You call these lazy learning. Why lazy?
Huh. Yeah, lazy because they don't really do the hard work of building a general model during a distinct training phase. They basically just store the training data.
They wait until you ask them something.
Precisely. When you present a new data point and ask for a prediction, then they get busy. They search through the stored training examples to find the ones that are most similar or nearest to the new point.
And base the prediction on those neighbors.
Exactly. They derive a local model or make a prediction based purely on those similar instances found in the database. No explicit generalization happens beforehand.
So K nearest neighbors, KNN, is the classic example here.
It is very intuitive. For a new point, find the K closest training examples in the feature space. If it's classification, predict the majority class among those K neighbors. If it's regression, predict the average value of those neighbors.
Simple idea. What are the pros and cons?
Well, it's easy to understand and implement. It makes no strong assumptions about the underlying data distribution, and it naturally handles multi-class problems.
Right.
But it can be slow, especially with large data sets, because it needs to calculate distances to all training points for each prediction. It can struggle if you have many irrelevant features, high dimensionality, and choosing the right value for aid, the number of neighbors, can be tricky and impact performance significantly. It's also sensitive to the scale of the features.
Okay. The source also mentions LVQ and SO briefly.
Right, learning vector quantization, LVQ, is sort of inspired by neural networks but still instance-based. Self-organizing maps, SOMs, are often used for visualization and clustering, projecting high-dimensional data onto a lower-dimensional grid while preserving topology.
And then there's support vector machines, SVMs. These have a reputation for being quite powerful, especially for classification.
They certainly do. SVMs are supervised learning models. Think of your data points plotted in space. For classification, SVM tries to find the best possible boundary, or hyperplane, that separates the different classes.
The best boundary. How does it define best?
It looks for the hyperplane that has the largest possible margin, the biggest empty space, between itself and the closest data points from each class.
Maximizing the gap.
Exactly. Those closest points that define the margin are called the support vectors, hence the name. They are the critical elements. The boundary depends only on them.
What makes them good?
They tend to be resistant to overfitting, especially when you have many features compared to data points. They can also handle nonlinear separation using something called the kernel trick, basically mapping data to higher dimensions where separation becomes linear. And the optimization problem they solve is convex, meaning you're guaranteed to find the global optimum.
Sounds great. Any drawbacks?
Well, feature scaling is usually necessary, making sure all features are on a similar numerical scale. Choosing the right kernel and its hyperparameters isn't always obvious. And importantly, standard SVMs don't scale very well to really massive data sets in terms of training time.
Okay, SVMs. Now, regularization algorithms. You mentioned these help prevent overfitting, like putting constraints on the model.
That's a perfect way to think about it. Overfitting is when a model learns the training data too well, including all the noise and random fluctuations. It fits the training data beautifully, but fails to generalize to new, unseen data.
It memorizes instead of learns the pattern.
Precisely. Regularization adds a penalty term to the model's loss function. This penalty discourages the model coefficients, the parameters it learns, from becoming too large. It forces the model to be simpler, smoother, and hopefully more generalizable.
And Lasso is a key example.
Yes, LASSO stands for Least Absolute Shrinkage and Selection Operator. It adds a penalty proportional to the absolute value of the coefficients. This is called L1 regularization.
What's the effect of that absolute value penalty?
It has a really interesting effect. It not only shrinks coefficients towards zero like other regularization methods, but it can actually force some coefficients to be exactly zero.
So it throws away some features entirely.
Exactly. It performs automatic feature selection, leading to simpler, sparser models. This is great for interpretability and can work well when you have correlated predictors or high-dimensional data.
What are the catches with Lasso?
It generally requires more data points, instances, than features. It can be sensitive to outliers. Data usually needs to be normalized first. It doesn't handle nonlinear relationships well inherently. And if you have a group of highly correlated predictors, Lasso tends to randomly pick just one from the group and zero out the others.
Okay, and ridge regressions, in other words.
Right. Ridge uses an L2 penalty proportional to the squared value of the coefficients. It shrinks coefficients towards zero, but doesn't typically force them to be exactly zero like Lasso does. It's good for handling multicollinearity.
Then there's ElasticNet. A mix of both.
Exactly. ElasticNet combines both the L1 penalty of Lasso and the L2 penalty of Ridge. This gives it some benefits of both. It can perform feature selection, like Lasso, but is also better at handling groups of correlated variables. It tends to keep or drop them together, and is more stable than Lasso in some situations.
Seems like a good compromise sometimes.
It can be. It often performs well, especially when you have many features, some possibly correlated. The downside is it adds another parameter to tune how much weight to give L1 versus L2.
And least angle regression LARS.
LARS is an interesting algorithm primarily for high-dimensional linear regression. It's an iterative method. It starts with all coefficients at zero and finds the predictor most correlated with the outcome variable. It then moves the coefficient for that predictor in the direction of its correlation.
Step by step.
Yes, it keeps going until another predictor has as much correlation with the current residual, the part of the outcome not yet explained. Then it proceeds in a direction that keeps the correlations equal for this active set of variables, adding more variables to the set as they become equally correlated.
Sounds efficient.
It can be, especially compared to some other methods for finding the entire solution path, how coefficients change as the model complexity increases. It's stable and handles correlated predictors somewhat gracefully. However, it can be sensitive to noise and might struggle with high multicollinearity in very high dimensions.
All right, that's regularization. Let's switch to decision tree algorithms. These seem quite intuitive, like a flowchart of questions.
Exactly. That's a great way to visualize them. A decision tree breaks down a data set by repeatedly asking simple questions about its features, splitting the data at each step based on the answers.
So you end up with branches and leaves.
Precisely. You start at the root node. Each internal node represents a test on an attribute, like, is the petal width 2 centimeters? Each branch represents the outcome of the test, yes or no, and each leaf node at the end of a path represents the final outcome or prediction, like, species is Iris setosa.
How does it decide which question to ask at each split?
It typically uses a metric like Giannini impurity or information gain, based on entropy, to find the split that results in the purest possible child nodes where the data points belong mostly to one class. It does this recursively.
And we have a bunch of variations. CART, ID3, C4.5, C5.0. What are the main differences?
They represent an evolution of the core idea. CART, classification and regression tree, is a general framework that can handle both categorical target variables, classification trees, and continuous ones, regression trees. It often uses Gini impurity.
And the others.
ID3 was an early influential algorithm, often using information gain. C4.5 improved on ID3 by being able to handle continuous attributes, missing values, and incorporating pruning.
Pruning, like trimming the tree.
Exactly. To prevent overfitting, pruning removes branches that provide little predictive power on unseen data. C5.0 is a further improvement on C4.5, often faster, more memory efficient, producing smaller trees and offering features like boosting and weighting for uneven error costs.
Okay, and Chi-H8E M5, conditional decision trees.
CHAID, chi-squared automatic interaction detection, uses statistical chi-squared tests to determine splits. M5 is known for building trees that predict continuous values, often producing smaller and more accurate models than standard regression trees, especially with high dimensions. Conditional decision trees use statistical significance tests within a conditional inference framework for splitting, avoiding potential biases found in some other methods.
So lots of ways to build these trees. Let's move to Bayesian algorithms.
Yeah.
Based on Bayes' theorem and probability, right?
Correct. Bayesian methods are fundamentally about updating our beliefs, probabilities, about something in light of new evidence. Bayes' theorem provides the mathematical framework for doing this.
And naive Bayes is the famous one. Why naive?
It's called naive because it makes a very strong, simplifying assumption that all the input features are completely independent of each other, given the class.
That sounds unlikely in real life.
Often, yes. Features are usually correlated to some extent, but the naive assumption makes the calculations much simpler. And surprisingly, naive Bayes classifiers often work remarkably well in practice, especially for things like text classification, spam filtering, topic categorization.
Even with the unrealistic assumption.
Even then, there are different flavors too. Gaussian naive Bayes assumes continuous features follow a Gaussian normal distribution. Multinomial naive Bayes is used for discrete counts, like word frequencies in documents.
Are there less naive Bayesian methods?
Oh yes, averaged one-dependence estimators, AODE, relax the independence assumption slightly. And Bayesian networks, also called Bayesian belief networks or BBNs, are much more sophisticated. They are graphical models that explicitly represent the probabilistic dependencies and independencies between a set of variables. They allow for more realistic modeling, but are more complex to build and learn.
Okay, probability-based learning. Now, clustering algorithms. Back to unsupervised learning, finding groups.
Exactly. Clustering algorithms are all about partitioning your data points into groups or clusters so that points within the same cluster are more similar to each other than they are to points in other clusters. And crucially, you don't tell the algorithm beforehand what the groups are or how many there should be, though some algorithms require you to specify the number of clusters.
What are the main ways to do this? K-means seems very common.
It is. K-means is an iterative algorithm. You start by guessing K-cluster centroids. Then you repeat two steps. First, assign each data point to the nearest centroid. Second, recalculate the position of each centroid based on the mean of all points assigned to it. You keep doing this until the centroids stop moving much.
Simple idea. Downsides.
You have to choose K beforehand. It's sensitive to the initial placement of centroids, and it tends to find spherical clusters of similar size, which might not fit all data structures. It's also sensitive to outliers because it uses the mean.
So K-medians is an alternative.
Yes, K-medians is similar, but uses the median instead of the mean to calculate cluster centers. This makes it more robust to outliers.
What about EM? Expectation maximization.
EM is a more general iterative algorithm used for finding maximum likelihood estimates when you have latent or unobserved variables. It's often used for clustering with probabilistic models, like Gaussian mixture models, where you assume each cluster is generated by a different probability distribution. It alternates between an expectation step, estimating the probability of each point belonging to each cluster, and a maximization step, re-estimating the parameters of the distributions.
And hierarchical clustering. That sounds like it builds a tree of clusters.
It does. Hierarchical clustering creates a nested hierarchy of clusters. There are two main types. Agglomerative, bottom-up, where you start with each point as its own cluster and iteratively merge the closest pairs of clusters, and divisive, top-down, where you start with all points in one cluster and recursively split them. This results in a tree diagram called a dendrogram, which you can cut at different levels to get different numbers of clusters.
Interesting. Okay, next. Association rule learning algorithms. Finding relationships, like people who buy bread also buy butter.
Exactly that kind of thing. These algorithms are used to discover interesting correlations or rules between items in large data sets, typically transaction databases like supermarket sales records. The rules are often expressed in an if-then format like diapers, beer.
Ah, a classic example. And the a priori algorithm is key here.
A priori is the foundational algorithm. It works by first identifying frequent item sets of items that appear together often enough above a certain support threshold. Then it generates association rules from these frequent item sets that also meet a confidence threshold, how often the rule holds true.
How does it find frequent item sets efficiently?
It uses the a priori property. Any subset of a frequent item set must also be frequent. This allows it to prune the search space significantly. It starts by finding frequent individual items, then uses those to generate candidate pairs, checks their frequency, then uses frequent pairs to generate candidate triples, and so on.
And ECLAT is another one.
Yes, ECLAT is often faster than a priori, especially for dense data sets. It uses a different data structure. TID sets lists of transactions containing an item set, and a depth-first search approach, which can be more memory efficient as it doesn't need to repeatedly scan the database in the same way a priori might. However, manipulating very long TID sets can become costly.
Got it. Now for the big one. Artificial neural network algorithms. Inspired by the brain, you said.
That's the inspiration, yes. ANNs are computational models composed of interconnected processing units called neurons, organized typically in layers. They are incredibly versatile and form the basis for much of deep learning. They can learn complex, nonlinear relationships between inputs and outputs for both classification and regression.
And the perceptron was the starting point.
It was one of the earliest, simplest types. A single perceptron takes multiple inputs, computes a weighted sum, and if that sum exceeds a threshold, it outputs 1, or fires, otherwise 0. It can learn to solve linearly separable problems.
But limited to straight-line divisions.
Exactly. The real power came with multi-layer perceptrons, MLPs. These have one or more hidden layers of neurons between the input and output layers. These hidden layers allow the network to learn much more complex, nonlinear decision boundaries. They use activation functions like sigmoid or ReLU to introduce nonlinearity.
And how do they learn? You mentioned backpropagation.
Right. Backpropagation is the most common algorithm for training MLPs. It works by comparing the network's output to the desired output, calculating the error, and then propagating that error backward through the network layer by layer. As it goes back, it calculates how much each connection weight contributed to the error and adjusts the weights accordingly to reduce the error next time.
So it learns from its mistakes, propagating the error back.
Precisely. Usually this weight adjustment is done using an optimization algorithm like stochastic gradient descent.
SGD.
Stochastic gradient descent is an iterative optimization method. To minimize the error, or loss function, it calculates the gradient, the direction of steepest descent based on a small random batch of training data, and then takes a small step in the opposite direction, steepest descent, to update the network's weights. It's computationally cheaper than using the whole data set for each step.
But it has downsides.
It can be noisy due to the random batches, so convergence might be slow or zigzaggy. Choosing the right learning rate, how big a step to take, is crucial and often requires tuning.
Okay. What about radial basis function networks, RBFNs?
RBFNs are another type of feed-forward network, typically with 3 layers: input, a hidden layer using radial basis functions as activation functions, and a linear output layer. The hidden layer often performs something like clustering on the input data. They can be faster to train than MLPs for some problems, but might require more hidden neurons.
Neural networks seem complex but powerful. And this leads us into deep learning algorithms, which are basically really big neural networks.
Essentially, yes. Deep learning uses neural networks with multiple hidden layers, sometimes hundreds or even thousands. This depth allows them to learn a hierarchy of features automatically, from simple low-level features in the early layers to complex high-level concepts in deeper layers.
And convolutional neural networks, CNNs or condens, are superstars for images.
Absolutely. CNNs are specifically designed for grid-like data, primarily images. They use special layers called convolutional layers that apply learnable filters across the input image. This allows them to automatically learn spatial hierarchies of features, edges, corners, textures, then parts of objects, then whole objects.
Why are they so good for images?
They exploit the spatial structure of images. They use parameter sharing, the same filters applied everywhere, which drastically reduces the number of parameters compared to a fully connected network, making them more efficient and less prone to overfitting. They basically build in assumptions about how visual information is structured.
But computationally expensive. Need lots of data.
Yes, training deep CNNs requires significant computing power, often GPUs, and typically large labeled datasets to perform well. Tuning them can also be tricky.
What about sequences like text or speech? That's where RNNs come in.
Exactly. Recurrent neural networks, RNNs, are designed for sequential data. They have connections that loop back on themselves, allowing information from previous steps in the sequence to persist and influence the processing of the current step. They have a kind of memory.
So they can understand context in a sentence, for example.
That's the idea. They can process inputs of varying lengths and theoretically capture dependencies across time. However, standard RNNs struggle with long-term dependencies, remembering information from many steps ago. This is known as the vanishing gradient problem.
Which led to LSTMs.
Right. Long short-term memory networks, LSTMs, are a special type of RNN specifically designed to overcome this problem. They have a more complex internal structure with gates, input, forget, output gates, that control the flow of information and allow the network to selectively remember or forget information over long sequences.
So they have better memory control.
Much better. They can learn long-range dependencies effectively. Gated recurrent units, GRUs, are another popular variant, slightly simpler than LSTMs, but often performing similarly. The trade-off is that these gated RNNs are even more computationally intensive to train.
Okay. What are autoencoders? They sound like they compress data.
They do, in a way. An autoencoder is typically an unsupervised feed-forward network where the target output is the same as the input. It has two parts: an encoder that compresses the input into a lower dimensional code or latent representation, and a decoder that tries to reconstruct the original input from that code.
What's the point of reconstructing the input?
The key is the compressed code learned in the middle. By forcing the network to reconstruct the input through this bottleneck, it learns a compact representation of the data's essential features. This can be used for dimensionality reduction, feature learning, or even generative tasks. There are variations like denoising autoencoders, learning to reconstruct clean data from corrupted input, and variational autoencoders, VAEs, which are generative models.
Interesting. Downsides.
They can be computationally expensive. The learned latent space might not be easily interpretable, and like other deep networks, they can overfit if not regularized properly.
Then we have deep Boltzmann machines, DBMs, and deep belief networks, DBNs. These sound more exotic.
They are types of generative models based on Boltzmann machines. A deep Boltzmann machine, DBM, is an unsupervised model with multiple layers of hidden units. Unlike some other networks, connections can be bidirectional, even within the same layer. They can learn complex probability distributions.
And DBNs.
A deep belief network, DBN, is typically composed of multiple stacked layers of restricted Boltzmann machines, RBMs, often trained layer by layer in a greedy, unsupervised fashion, followed by supervised fine-tuning. They were influential in the resurgence of deep learning, showing how deep networks could be trained effectively.
Complex stuff. Let's move to dimensionality reduction algorithms. Why reduce dimensions? You mentioned the curse of dimensionality.
Right. When you have a huge number of features, dimensions, compared to the number of observations, algorithms can become less effective. Distances between points become less meaningful, models can overfit easily, and computation gets very expensive. That's the curse. Dimensionality reduction aims to reduce the number of features while preserving as much important information as possible.
To make things more manageable and potentially improve performance.
Exactly. It compresses the data, can speed up computations, remove redundant features, and sometimes help with multicollinearity.
And principal component analysis, PCA, is the workhorse here.
It's certainly the most widely known linear technique. PCA transforms your original correlated features into a new set of uncorrelated features called principal components. These components are ordered so that the first few capture the largest possible variance in the original data.
So you can often keep just the first few components and discard the rest.
That's the idea. You capture most of the information, variance, with fewer dimensions. However, PCA is sensitive to the scale of the original variables, so you usually need to standardize your data first, and the resulting components might not always be easily interpretable.
What are some other methods? PCR, PLSR.
Principal component regression, PCR, simply performs linear regression using the principal components as predictors instead of the original features. Partial least squares regression, PLSR, is another technique related to PCA and regression that tries to find components that are relevant for predicting the outcome variable, not just capturing variance in the predictors.
NDS.
Multidimensional scaling, MDS, is more focused on visualization. It takes a matrix of distances or dissimilarities between items and tries to create a map, usually in 2D or 3D, where the distances between points on the map reflect the original dissimilarities as closely as possible. Helps you see relationships visually.
LDA also reduces dimensions, but with classes in mind.
Yes, linear discriminant analysis, LDA, is a supervised technique often used for dimensionality reduction before classification. Unlike PCA, which just looks at variance, LDA explicitly tries to find a lower dimensional space that maximizes the separability between known classes.
So it's better if the goal is classification.
Often, yes. There are also variations like mixture discriminant analysis, MDA, and quadratic discriminant analysis, QDA, which relax some of LDA's assumptions, like allowing different covariance structures for each class.
So lots of benefits to reducing dimensions.
Data compression, faster computation, less overfitting risk.
But potential downsides, too.
Definitely. You inevitably lose some information. Linear methods like PCA might miss important nonlinear structures, and deciding how many dimensions to keep isn't always obvious. It's often a trade-off.
Okay, final major category. Ensemble algorithms. Combining models for better results.
Precisely. Ensemble methods are meta-algorithms that combine the predictions from multiple individual machine learning models, often called base learners, to produce a final prediction that is hopefully more accurate and robust than any single model could achieve alone.
Like wisdom of the crowd.
Sort of. The main ideas are typically to reduce variance, like in bagging, or reduce bias, like in boosting, or just improve overall predictive performance, like in stacking.
Let's start with boosting, transforming weak learners into strong ones.
That's the core idea. Boosting algorithms train models sequentially. Each new model added to the ensemble focuses on correcting the mistakes made by the models trained so far. It gives more weight to the data points that previous models misclassified.
So it learns from errors. AdaBoost is a classic example.
Yes, adaptive boosting, AdaBoost, iteratively trains weak learners, often simple decision trees called stumps, and gives more weight to instances that were misclassified in the previous iteration. The final prediction is a weighted vote of all the weak learners.
And gradient boosting machines, GBMs.
GBMs are another powerful boosting technique. They also build models sequentially, but instead of reweighting instances like AdaBoost, each new model tries to predict the residuals or errors of the preceding ensemble. It fits the new model to the negative gradient of the loss function, hence the name gradient boosting.
Seems powerful, but potentially complex.
They often achieve state-of-the-art results on many structured data problems, but they can be prone to overfitting if not carefully tuned.
Okay, that's boosting. What about bagging? Bootstrapped aggregation.
Bagging takes a different approach. Instead of sequential training, it trains multiple base models in parallel, independently of each other. The key is that each model is trained on a different random subset of the original training data drawn with replacement. This is the bootstrapping part.
So each model sees a slightly different view of the data.
Exactly. Then, to make a final prediction, bagging simply aggregates the predictions from all the individual models, usually by averaging for regression or majority voting for classification, the aggregation part.
What's the main benefit of bagging?
Its primary benefit is reducing variance. By averaging predictions from models trained on different data subsets, it smooths out inconsistencies and makes the overall prediction more stable and less sensitive to the specific training data. It helps reduce overfitting.
Any drawbacks?
Well, the resulting ensemble model is less interpretable than a single model, like a decision tree. If the base models themselves are heavily biased, bagging might not fix that. And training many models can be computationally expensive.
And random forest is a famous bagging method.
Yes. Random forest is essentially an extension of bagging specifically for decision trees. It adds another layer of randomness. Not only is each tree trained on a bootstrap sample of the data, but at each split point within a tree, only a random subset of features is considered for making the split.
Extra randomness. Wow.
This further decorrelates the trees in the forest. If one feature is very strong, bagging might lead to many trees using that feature near the root, making them similar. By restricting the feature choice at each split, random forest forces the trees to explore other features, leading to more diversity in the ensemble and often better performance.
So random forests are generally pretty good.
They are known for performing very well on a wide range of problems, often with minimal tuning. They handle large databases, both regression and classification, are resistant to overfitting, can provide measures of feature importance, and don't require feature scaling. They are a very popular go-to algorithm.
Okay. What about weighted average blending?
This is a simpler ensemble technique where you just combine the predictions of several different pre-trained models by taking a weighted average. The challenge is finding the optimal weights.
And stacking. Stacked generalization.
Stacking is more sophisticated. It involves training multiple different base models, like an SVM, a random forest, a KNN. Then, instead of simple averaging, you train a second-level model called a meta-learner, whose job is to learn how to best combine the predictions from the base models to make the final prediction.
So a model learns how to combine other models.
Exactly. The inputs to the meta-learner are the predictions made by the base models on the training data, or often on out-of-fold predictions to avoid leakage. Stacking can sometimes achieve better results than any single base model or simple averaging, but it's more complex to set up and train.
Finally, gradient-boosted regression trees, GBRT. We mentioned GBMs. Is this related?
Yes, GBRT is just another name for gradient boosting machines when the base learners being used are decision trees, specifically regression trees. As we said, they build an additive model, combining judgments from a sequence of trees, linking back to gradient descent optimization. They're very powerful for predictive analytics, handling numerical features well and capturing nonlinear interactions.
But maybe not ideal for all data types.
Right. They might not be the best choice if you have very high-dimensional categorical features, as standard implementations can struggle with those.
Wow, that's a huge tour of algorithms. So going back to the choice, the source just says, understand your data. Seems crucial but brief.
It's the absolute foundation. Knowing your data's characteristics, size, type, quality, distribution, relationships is paramount before you can even start thinking about which algorithm might be appropriate. Everything else follows from that understanding.
Right, so let's see these in action. The source looked at predicting football match results.
Yeah, this was interesting. They took data from 5 big European leagues, Premier League, La Liga, Serie A, etc., using stats like shots, fouls, corners, cards for home and away teams.
And they compared different algorithms.
Right. They looked at accuracy both when predicting just home-away win, excluding draws, and when predicting home-away draw. They cited lots of previous work using things like LogicBoost, Random Forest, Bayes nets, ANNs.
What did this study find?
Across the individual leagues, LMT, logistic model trees, and SMO, sequential minimal optimization, an algorithm for training SVMs, often came out on top. But the really interesting part was when they combined all 5 leagues into one data set.
Did one algorithm stand out then?
SMO did. It gave the best overall accuracy, both with draws excluded around 81.7% and included around 63%. Manual feature selection also pointed to shots on target and red cards as being highly correlated with results.
So combining league data helped, and SMO was robust. Fascinating. What about predicting tennis matches? This used indirect stats.
Yes, this was clever. They took data from 4 Grand Slams in 2013, but deliberately removed stats that directly indicate the winner, like set scores or total points won. They kept things like aces, double faults, points won on first serve, break points created.
Stuff that doesn't guarantee a win but reflects playing style or pressure.
Exactly. The goal was to see if patterns in these indirect stats could predict the winner. They used Weka software and tried various classifiers.
And the results?
Surprisingly high accuracies. Using algorithms like Simple Logistic, Multiclass Classifier, and Random Forest, they got accuracies often above 90% for both men's and women's matches when analyzing tournaments individually or combined.
90% just from indirect stats. That's huge.
It is. They even found slight improvements when training on one tournament and testing on another, though training on men's data to predict women's or vice versa generally lowered accuracy.
So it's not quite ready for betting on future matches.
Not yet, as they point out. It's more about analyzing patterns that correlate with winning. Future work would need real-time stats, maybe weather, injuries, surface type. Much more complex. Predicting tennis, especially between top players, is still really tough.
Makes sense. Okay, let's shift to business and science. Estimating used car prices. That seems like a classic machine learning task.
It is, but tricky because prices on classified sites like the eBay data they used are set somewhat subjectively by sellers. Plus, there are tons of parameters.
What did they find worked best on their large data set, about 370,000 cars?
They compared things like linear regression and lazy KNN, like K nearest neighbors, with tree-based algorithms. The trees specifically, Random Forest and Random Tree, performed significantly better, showing lower error and higher correlation with the actual prices. KNN was comparable.
And what factors mattered most? Was it the brand?
Interestingly, no. While Volkswagen was the most common brand, attribute selection suggested factors like year of registration, gearbox type, power, PS, fuel type, and then brand were more dominant predictors of price.
So the specs mattered more than the badge in this data set.
Seems so. They also found that performance improved when they focused just on the Volkswagen data, likely because it was a more uniform subset.
Okay. Next, forecasting the popularity of online news. That sounds valuable but hard.
Very hard. Predicting clicks or shares depends on so many things: content, timing, real-world events, who shares it. This study looked at predicting whether an article would be popular, above the median number of shares, using features available before publication or very early on.
What algorithms did they try?
They used supervised learning, focusing on an artificial neural network, ANN, which achieved about 64.4% accuracy in classifying popular versus unpopular news using a mix of features. They also tested others in Weka.
Did anything beat the ANN?
Bayesnet achieved similar accuracy, around 70% on some metrics, close to the ANN, but was significantly faster to train, about 4 seconds, versus potentially much longer for the ANN. Hofting Tree was even faster, but less accurate.
So a trade-off between speed and accuracy. Bayesnet seemed like a good balance.
It did. They concluded that future work needs more sophisticated content analysis and features to really push the accuracy higher.
Right. Predicting student performance using fuzzy logic. This sounds like risk management for scholarships.
Exactly. Can we predict which students are likely to succeed based on past data, demographics, social factors? They framed it as needing an impartial AI approach for large data sets.
And they used fuzzy logic.
Yes, specifically an adaptive neurofuzzy inference system, ANFIS. They ran into issues initially when feeding too many inputs into one block, getting high error rates,
How did they fix that?
by breaking the problem down. They divided the inputs into smaller processing blocks, like 4 inputs, 8 inputs, or 3 and 7 inputs, and found this significantly reduced the prediction errors. Finding the optimal number of inputs per block was key.
So modularity helped.
It did. Their final system used JavaScript and Node.js to handle data, called MATLAB for the fuzzy logic processing, using these pre-trained blocks, combined the outputs with a weighted average, and sent a success percentage back.
Interesting architecture. They noted needing faster processing, though.
Yes, and suggested converting MATLAB code to C for speed and wider use, and using larger localized data sets for better precision.
Okay, last one in this section. Credit card fraud detection, a critical area.
Hugely important. Financial losses are massive, and fraudsters are always evolving. Machine learning is vital here because fraud transactions are often rare anomalies in vast amounts of genuine transactions. Simple rules don't cut it.
What did the literature say works?
Neural networks were highlighted as successful, detecting more fraud with fewer false alarms than rule-based systems. Other methods like naive Bayes, KNN, and logistic regression have been used, but performance can depend heavily on how you handle the imbalanced data, way more genuine than fraudulent transactions. KNN was noted as potentially performing well.
And what did this specific study test on their synthetic dataset?
They used Weka to test naive Bayes, neural networks, decision tree J48, and random forests using cross-validation.
Woo one.
In terms of raw accuracy, the neural network was highest, 99.92%, but it took a very long time to process. Random forest was a very close second in accuracy, 99.96%, and significantly faster.
But accuracy isn't everything in fraud, right? False negatives are bad.
Exactly. Missing a fraudulent transaction, a false negative, is usually much worse than flagging a genuine one by mistake, a false positive. Random forest had significantly fewer false negatives than the other methods, making it the top performer overall in their evaluation, even with slightly more false positives.
So random forest offered the best practical balance. Makes sense. Now let's turn to medicine, heart disease prediction.
Yes, another critical application, using patient data to predict the likelihood of heart disease. This study compared several supervised algorithms, SVM, random forest, decision tree, logistic regression, naive Bayes.
What data did they use?
The well-known Cleveland Heart Disease Database from the UCI repository. It has about 300 records, 13 features like age, sex, chest pain type, cholesterol, blood pressure, ECG results, etc., and a class label indicating presence or absence of heart disease.
What were the key results?
SVM and logistic regression came out on top, both achieving around 87.9% accuracy. Naive Bayes was next at 83.2%, and the decision tree lagged a bit at 71.4% accuracy on this particular dataset and setup. Precision and recall varied too, with logistic regression having very high recall, finding most of the actual positive cases.
So SVM and logistic regression seemed most promising there. Finally, big data in mental health diagnosis and treatment. This sounds both promising and challenging.
Extremely challenging, but with huge potential. Mental illness affects billions, yet diagnosis is often slow, treatment inaccessible, and stigma remains high. The idea is that machine learning applied to large data sets could help identify patterns, risk factors, and personalized treatments much earlier.
What kind of data are we talking about?
It's varied. Electronic health records, sensor data from smartphones, tracking activity, location, potentially mood indirectly, social media posts, analyzing language for sentiment or distress signals, survey data.
But the source mentioned issues with data.
Yes, a major recurring theme. Data is often collected for other purposes and might be incomplete, unreliable, or biased, for example, not representing all demographics. Missing data was a specific problem noted in analyzing data from 2016-2019. You need good, relevant data for any algorithm to work well.
So big data offers potential but needs careful handling and awareness of limitations.
Absolutely. There's a need for better data collection focused on specific research questions, transparency, and addressing ethical concerns. But the potential to use ML for earlier diagnosis, monitoring treatment effectiveness, developing new therapies, and identifying risk factors is immense. Algorithms like naive Bayes, KNN, logistic regression are being explored, along with analysis of app reviews, social media, and health records.
A field with massive potential impact, but still grappling with data challenges.
Definitely.
Okay, we've journeyed through an incredible landscape of machine learning algorithms. We've looked at how they learn supervised, unsupervised, and so on, and what they do, regression, classification, clustering.
And we've seen them applied in so many areas. Predicting football and tennis, estimating car prices, gauging news popularity, student success, detecting fraud.
Right, and then into critical medical fields like heart disease and the huge potential and challenges in mental health.
Yeah, it's really broad. One thing that struck me was that SMO algorithm popping up as so effective for the combined football league data. You might not expect one algorithm to generalize quite so well across different national styles of play represented in that data.
That is interesting. And the used car example brand being less important than specs on that large data set kind of defies common assumptions, doesn't it?
It does. Shows how data can sometimes reveal counterintuitive insights, or maybe just reflects the specific market captured in that eBay data.
So for you listening, we hope this deep dive has armed you with a clearer understanding of these algorithms, cutting through some of the hype and giving you a real sense of how they work and where they're used.
It's about getting that foundational knowledge efficiently, seeing the logic behind the tools that are increasingly shaping our world.
Which leads to a final thought. As these algorithms get better, and we gather more diverse data, maybe from sensors, maybe from online interactions, what completely unexpected connections might we find? Could analyzing, say, commuting patterns reveal insights into economic trends, or could patterns in online game behavior tell us something about cognitive health? Where might the next surprising application of machine learning come from?
That's a great question to ponder. What seemingly unrelated data holds the key to the next big insight?
Something to think about. If any particular algorithm or application caught your interest today, definitely explore it further. There's always more to learn in this field.